Friends, I am Dr. Tamrakar from Bharatiya College of Agricultural Engineering, Durg. I will teach theory of machine of BTech first year, second semester class. Dear students, today we will solve one numerical. In a mechanism as shown in figure 7.15, the various dimensions are OC equal to 125 mm, CP equal to 500 mm, PA equal to 125 mm, AQ equal to 250 mm, and QE equal to 125 mm. These are the dimensions of the mechanism, and this is the arrangement of the mechanism shown in the figure. The cider P translates along an axis which is 25 mm vertically below point O. The crank OC rotates uniformly at 120 rpm in anti-clockwise direction. The bell crank lever AQE rocks about the fixed center Q. Draw the velocity diagram and calculate the absolute velocity of point E of the lever. So we have to solve this question. Here this bell crank lever AQE rotates this rocks, so the point E move. So here the data given: NCO equal to 120 rpm, so omega CO equal to 2 pi into 120 by 60, that is 12.57 radian per second. OC equal to 125 mm equal to 0.125 meter. We know that linear velocity of C with respect to O, or velocity of C because O is a fixed point, VCO equal to VC into omega CO into OC. VC equal to omega CO into OC equal to 12.57 into 0.125 equal to 1.57 meter per second. First of all, draw the space diagram as shown in figure 7.16a to some suitable scale. Left side A is the space diagram. Then velocity diagram 7.16b. To draw the velocity diagram, first point, since the point O and Q are fixed, here point O and Q both are fixed, therefore these points are taken as one point in the velocity diagram. तो एक ही पॉइंट पर इसने O और Q को बी राइट साइड वाले डायग्राम पे O और Q को एक जगह पर ले लिया हुआ है, क्योंकि ये पॉइंट फिक्स हैं आपके. ठीक है. फ्रॉम O ड्रॉ वेक्टर OC. O से OC लिया, दैट इज परपेंडिकुलर टू OC ऑफ स्पेस डायग्राम. ठीक है. लेफ्ट साइड में स्पेस डायग्राम है, उसके परपेंडिकुलर OC ले लिया. ये भी किसी रेशो पे ले लिया हुआ, जिस रेशो पर यहाँ पर हमको वैसे डायग्राम बनाना है. To represent the velocity of C with respect to O, or velocity of C such that vector OC equal to VCO equal to VC equal to 1.57 meter per second. Second point, from point C draw vector CP perpendicular to CP to represent the velocity of P with respect to C, that is VPC. Okay, and from point O, draw vector OP parallel to the path of motion of slider P. ठीक है, अब ये स्लाइडर के पैरेलल मोशन लगाया OP with which is horizontal to represent the velocity of P, that is VP. Therefore, vector CP and OP intersect at point P. Third point, from point P, draw vector PA perpendicular to PA to represent the velocity A with respect to P, that is VAP, and from point Q, draw vector QA perpendicular to QA to represent the velocity of A, VA. The vector PA and QA intersect at A. Now draw vector QE perpendicular to vector QA in such a way that QE by QA equal to QE by QA. By measurement, we find that the velocity of point E, VE, vector OE equal to 0.7 meter per second. So, you have to solve different questions that have been asked in the university examination and practice that questions so that you would be able to solve the questions asked in the examination. Next, we will solve one more example, that is example 7.7. A quick return mechanism of the crank and slotted lever type shaping machine is shown in figure 7.17. In the right side it has been shown. The dimension of various links as follows: O1, O2 equal to 800 mm. This bottom is O2 and O1, O2 is 800 mm. O1B, this O1B is 300 mm. O2D is 1300 mm. DR is 400 mm. The crank O1B makes an angle 45 degree with vertical and rotate at 40 rpm in the counterclockwise direction. O1B. Find first point velocity of ram R or velocity of cutting tool, and second point angular velocity of link O2D. These two things we have to calculate. For this, the data given are N BO1 equal to 40 rpm. So omega BO1 2 pi 40 by 60, that is 4.2 radian per second. Since the length of crank O1B equal to 300 mm equal to 0.3 meter, therefore velocity of B with respect to O1, simply the velocity of B, because 1 is fixed, a fixed point. Here O1 is fixed point. So V BO1 equal to VB equal to omega BO1 multiply O1B, that is 4.2 into 0.3 equal to 1.26 meter per second, that is perpendicular to 1B. To draw the velocity of ram, first point, find out the velocity of ram. First of all, draw the space diagram to some suitable scale as shown here in figure 7.18a. 7.18a. Now, the velocity diagram. First point, since O1, O2 are fixed, therefore these points are marked as one point in the vector. This is the velocity diagram, right side, and left side is space diagram. Here O1, O2 are fixed, therefore these points are marked as one point in the velocity diagram. Therefore vector O1b perpendicular to O1b to some suitable scale to represent the velocity of B with respect to O1, or simply velocity of B such that vector O1b equal to VBO1 equal to VB equal to 1.26 meter per second. Second point, from point O2 draw vector O2c perpendicular to O2c to represent the velocity of coincident point C with respect to O2, or simply velocity of C, that is VCO2 equal to VC, and from the point B draw vector BC parallel to path of motion of the sliding block, this sliding block, which is along O2D, to represent the velocity of C with respect to B, that is VCB. The vector O2C and BC intersect at C. Third point, since the point D lies on O2 produced, therefore divide the vector O2C at D in same ratio as D divides O2C in space diagram. In other words, CD equal to O2D, CD by O2D, CD by O2D equal to CD by O2D. Fourth point, now from point D, draw vector dr perpendicular to dr to represent the velocity of r with respect to d, that is VRD. And from point O1, draw vector O1r parallel to path of motion of r, which is horizontal, to represent the velocity r, that is VR. The vector dr and O1r intersect at r. Now, second point, angular velocity of link O2D. By measurement from velocity diagram, we find that the velocity of D with respect to O2, or velocity of D, V dO2 equal to Vd equal to V vector O2D 1.32 meter per second. From here, this diagram, we know the length of link O2D equal to 1300 mm equal to 1.3 meter. Therefore, angular velocity of link O2D, that is omega dO2 equal to V dO2 by O2D 1.32 by 1.3 equal to 1.015 radian per second, that is anti-clockwise about O2. This is the angular velocity of link O2D. This picture shows prototype of an industrial steam engine before to the invention of electricity. Steam engine used to provide the power needed to turn wheel in the factories. This picture is given some additional information. Next, we will solve one more numerical. In the mechanism as shown in figure 7.19, the crank O1A rotates at a speed of 60 rpm in a clockwise direction, imparting vertical reciprocating motion to crank R by means of two-thread coordinate Q. O1 and O2 are fixed center and the slotted bar BC and quadrant Q are rocking on O2. This is the arrangement of the mechanism and dimensions are here. Now we have to determine first the linear speed of the crank when the crank makes angle 30 degree to the horizontal, and second the ratio of the times of lowering and raising the rack, and third point the length of stroke of the rack. So here the data are given: n AO1 equal to 60 rpm or omega AO1 equal to 2 pi 60 by 60, that is 6.28 radian per second. Since crank length O1A equal to 85 mm, therefore velocity of A with respect to O1 or velocity of A, because O1 is a fixed point, तो यहाँ पर हमको पता है O1 आपका फिक्स है और O2 भी आपका फिक्स है, ठीक है। यहाँ पर हमने वेलोसिटी ऑफ AO1 निकाल लिया, that is equal to VA equal to omega AO1 into multiply O1A, that is 6.28 into 85, that is equal to 534 millimeter per second, perpendicular to O1A. Here we have to draw the space diagram from this mechanism and vector diagram. For making the vector diagram, we have to follow the points. First point, linear speed of the rack. First of all, draw the space diagram to some suitable scale as shown in figure. Now the velocity diagram is drawn as discussed below. First point, since O1 and O2 are fixed points, therefore they are marked as one point in the velocity diagram. From point O1, draw vector O1A perpendicular to O1A to some suitable scale to represent the velocity of A with respect to O1, or simply velocity of O, such that vector O1A equal to VAO1 equal to VA equal to 534 mm per second. Second point, from point A, draw vector AD parallel to the path of motion of D, which is along the slot in the link BC, to represent the velocity D with respect to A, that is VDA, and from point O2, draw vector O2D perpendicular to line joining the point O2 and D, because O2 and D lie on the same link, to represent the velocity of D, that is VDO2 equal to VD. The vector AD and O2D intersect at D. The point A represents the point on the crank as well as on the siding block, where the point D represents the coincident point on the lever O2C. By measurement we find that VDO2 equal to VD equal to vector O2D equal to 410 mm per second and O2D equal to 264 mm. We know that angular velocity of the quadrant Q, omega Q, equal to VDO2 by O2D equal to 410 by 264 equal to 1.55 radian per second clockwise about O2. Radius of quadrant Q, RQ, equal to 50 mm. Since the rack and the quadrant have rolling contact, therefore the linear velocity at point of contact will be same as that of quadrant. So linear speed of rack VR equal to omega Q into RQ equal to 1.55 into 50, that is 77.5 millimeter per second. Second point, ratio of the time of lowering and raising the rack. The two extreme positions of the rack AB are when the tangent to the circle with center O1 is also a tangent to the circle with O2 as shown in figure 7.21, the side figure. The rack will be raising when the crank moves from A1 to A2 though an angle alpha, and it will be lowering when crank moves from A2 to A1 though an angle beta, since the time of lowering and raising the rack is directly proportional to the respective angle. Therefore, time of lowering by time of raising beta by alpha, that is 240 by 120 equal to 2 by measurement. Third point, length of stroke of the rack. By measurement, we find that angle B1, O2, B2 equal to 60 degree. That is equal to 60 to pi by 180. So this is 1.047 radian. We know that length of stroke of the rack equal to radius of quadrant multiply angular rotation of the quadrant in radians equal to RQ multiply angle B1, O2, B2 in radian equal to 50 into 1.047 equal to 52.35 mm. So you have to solve different numericals and practice on doing this numericals. That will be helpful for you. Thank you.